Hi, I'm Sam. Oh my gosh, this is loud. So I'm Sam, and today I'm going to be presenting work with my co-authors, John Lee and Stephen Holtzen, titled Multi-Language Probabilistic Programming. So Karthik gave you a small taste of probabilistic programming languages, and so in probabilistic programming languages, the semantics of our programs are inference, and there's a very large design space that inference promotes. There's a funny little feature about these probabilistic programming languages, which is that if we want to have a small addition to these languages, it can have a huge impact on inference performance. There's kind of this expressivity, tractability trade-off that happens where we want to write models that better represent real-world processes. But at the same time, the more we restrict these languages, the stronger the guarantees are that we can make for fast inference. So we're going to take a quick look at this restrictive probabilistic programming language called DICE. Now, DICE supports probabilistic conditioning, as you would expect. It's very good at handling complex discrete structures, and it gives us fast, exact answers. At the same time, if you want something like a uniform distribution or a Poisson distribution or even just like an unbounded loop, this is not the language for you. So let's take a quick look at these restrictions. So in this little case study, we're interested in the probability that a packet will traverse some probabilistic, some router network that's defined using a probabilistic routing protocol and reach some end node. So this is very straightforward to represent using DICE. And we'll take each node and we'll model it as a series of flip statements. And if the node returns false, then the packet will be dropped. So as I pointed out, this is straightforward in DICE. And under the hood, it's using something called knowledge compilation to compactly represent these distributions. But if we want to make this problem a little more realistic and instead ask the question, given an unknown number of incoming packets, how many packets will arrive at our destination, then something funny happens. So here's a standard way to model this kind of probabilistic program. We're going to model the incoming number of unknown packets as a Poisson distribution, and then for each packet, we'll query the probability of a successful traversal, and we'll total that, or we'll sum those and return the total to get our random variable. Now, as I pointed out, DICE can't handle any of these features in this new function, but if we switch to a language like Pyro, then we're all clear. Unfortunately, though, we're going to lose the benefits of fast inference that DICE was providing for us when we went to write this network function. So what if we could use both languages? What if we could use Pyro for those continuous distributions and get access to these flexible, expressive primitives, and at the same time use DICE to model the network function and get the benefits of knowledge compilation? Now, that's a very sort of similar situation to something we already know about in PL. We already have low-level languages and high-level languages, and there's a rich body of research surrounding interoperation already. But there is not really a probabilistic analog when it comes to inference. So to address this, we come up with multi-language probabilistic programming. And our contributions are that we solve this challenge of interoperation between an exact and an approximate probabilistic programming language. We prove this sound by providing a high-level specification and showing that it is soundly refined by a low-level model that denotes the particular inference strategies. And we also provide a reference implementation to showcase this trade-off between sample efficiency and sample quality. In a nutshell, a multi-language might look like this. We might have two grammars where we have some perhaps typed language on one side of this multi-language and maybe an untyped language on this other side of the multi-language. And we'll take each grammar and we'll extend them with boundary expressions to perform this interoperation. And in our setting, we define disc and cont, where disc is a discrete probabilistic programming language that performs exact inference. And cont is a probabilistic programming language that performs approximate inference with sampling and has access to both discrete and also continuous random variables. So when we actually look at a distribution in flip, let's say, what we're going to do is we're going to compile this this data structure called a binary decision diagram, or a BDD. And this, for all intents and purposes, you can just think of as a fancy data structure to precisely represent the distribution that we're interested in. Alternatively, if we're in Kant, we're going to sample distributions immediately. And so this flip statement will evaluate to either true or false. And we'll have to repeat this process many times and use a number of executions to approximate the semantics of our program. If we want to look at something slightly more complex, here we define two coins, x and y, and we're interested in the probability that y is true, given x or y being true. And so in disk, we'll return that BDD that represents y, but we'll also compile this thing called the accepting formula, which is constructed through the observe expressions and represents the conditional probability. In Kant, we will return weighted samples of y, where the weights are drawn from those observed statements, here returning 1 if x or y is true, or 0 if that is false. Now, both programs shown denote the probability that y is true, given x or y is true, and specifically the semantics of both programs is 1/2 in this case. So we want to perform sound interoperation, and to do this, we identify two invariants, namely sample consistency and also importance weighting. So here's a disk program where on line 1, we define some flip statement, some flip expression, and bind it to x. And then we access that free variable on line 2, alias it to y. And then again, we access that free variable x and can join it to y in the Kant language. So as I pointed out, disk produces distributions and Kant samples those distributions. So the first time we access that x, we'll either evaluate to true or false. But the second time we evaluate x, we better make sure that that is consistent with all previous statements. So in our boundaries, we need to ensure that this sampling effect only happens once so that this interoperation is correct. And we do this by conjoining an extra condition onto the accepting formula during interoperation. We also require this thing called importance weighting. So here's that same program that I showed you before. And the semantics of this program is 1/2. But what we've done is we've introduced more boundary expressions to sort of make this more exciting. On line 1, we're going to 1/2 of the time sample x to be true. And we'll produce this disk program. And the semantics of this program is that we're interested in the probability of y, which is 1/2 in this case. The other half of the time, we're going to sample x to be false. And here, the resulting program has the semantics of 1 because we're interested in the probability that y is true, given that y is true. It's always 1. So to actually use these results, we need to sample for some fixed number of times. Let's say that's 100. So perhaps 50%, or for 50 executions, we get 1/3. 50 executions, we get 1. And if we actually just take this naive expectation, we get the wrong answer. So what we really need is some kind of corrective factor here. And so we'll take the weighted expectation, where these weights are called importance weights. And we need to define a correct importance sampling or importance weighting scheme. So the importance weights come from these observe statements. Here, an observe of true corresponds to a weight of 1, and the observe of y corresponds to a weight of 1/3. And this gives us the answer we expect. So we also prove this sound. And we do this by defining a high-level model, which denotes the semantics of our programs without paying attention to the inference processes that we're operating over. Specifically, these are the ground truth semantics, and it's uniform over the multi-language. And then we also define a low-level model, which is the denotational semantics that capture the specific details of inference. We show that the high-level model is refined by the low-level model, and basically that importance samplers defined in the high-level model are equivalent to ones defined in the low-level model. So if we take a look at that program from before, what that means is that the high-level semantics are going to take syntactic flip statements in both cont and disc, and those will denote semantic flip statements. And then observe statements will denote this semantic score. And this is operating under, this is a pretty standard thing to do, and this comes from the Staten et al. Paper in LIX 2016. And the semantic domain for all of this is dist plus writer monad, where the writer is accumulating those importance weights. We also have this low-level model, and this is just building up the intuition, or like the denotation of those two inference strategies that I kind of touched on. These are also operating under the dist plus writer monad, and the disk, the denotation for the disk expressions will be knowledge compilation, and for the cont language, this will be likelihood weighting. And when we reach a boundary expression, we'll just switch over to the other low-level model. So we also provide a reference compiler and have evaluations. And so here's one of our two tables. Specifically, here we're evaluating that arrival model from the motivating example. We have some discrete Bayes nets, and we also include in this table an undirected gossip protocol as a probabilistic model, which is quite adversarial to knowledge compilation. We're interested in evaluating two metrics, sample quality, which is measured as L1 distance from a known solution, and sample efficiency, which is measured by the wall clock time for taking 1,000 samples. Our baseline is cont, which performs no interoperation. And what we do to define multi-PPL programs is we're trying to insert boundary expressions that will heuristically produce the highest quality samples while still being practical and efficient. And what we see is that inserting these boundaries allows for a trade-off between sample quality and time per sample. Yeah, I'm happy to take questions now.
Okay, any questions?
Hi, thank you for the talk. So in your experiments, how did you choose the boundaries between disk and cont, given some of the Bayesian nets were expressible in both the languages? Mm-hmm. So what were the heuristics behind those?
Yeah, we tried to just encapsulate as much of the discrete random variables in disk as possible, but obviously we can represent those discrete Bayes nets fully in disk, and evaluating 1,000 samples, reevaluating that program 1,000 times is inefficient, so there's like just a heuristic balance to make sure that that's within like a reasonable expectation of wall clock time.
So you kind of try to balance between the wall clock time and the accuracy?
Yes, yeah.
Oh, okay, thank you.
Okay. Maybe one last question while you switch. Mm-hmm.
Cool, thanks for a very interesting talk. So I was curious, so the way I'm used to thinking about interoperation between probabilistic programming languages is through the idea of like black box probabilistic programs, right? So having probabilistic programs, each of them guaranteed that they satisfy a certain API or spec where you can either sample from it or evaluate the probability of a certain sample. And then as long as all languages satisfy the API, you can compose them through that lens. So I'm kind of curious with this like deeper language code level integration that your system allows, like what kinds of additional flexibility do you think it enables?
That's very interesting. I think we should probably talk about that offline. That's yeah.
All right, thanks.
Okay, let's thank the speaker again.